Okay, we should be live now.
So everyone, welcome. So today we're going to hear a presentation by Dr. Sumeh Haidari. She's a postdoctoral fellow at the Johns Hopkins University Laboratory for Computational Audio Perception. She works at the intersection of artificial intelligence, cognitive science, and computational neuroscience. Her primary area of research falls within cognitively informed artificial intelligence. She received her master's and PhD degrees from the University of Memphis in computer engineering in 2016 and 19, respectively. Her dissertation focused on active perception by interaction with other agents in partially observable environments. And during her PhD and postdoc, she had the opportunity to work on interdisciplinary projects funded by NSF and NIH. So with that, let's welcome Dr. Haidari.
Hello, everyone. Thank you for giving me the opportunity to be here and share my research with you. Today, I'm going to talk about active perception in cognitively informed artificial intelligence. But what is active perception? Some evening long ago, our ancestors looked into the sky and found some patterns in the stars. They had probably seen the stars several times, but this was the first time their eyes caught the patterns. What did they need to find the patterns? Of course, they needed to find a dot and another dot to link the dots. And the most important thing was to hypothesize the pattern. Something like, those dots look like part of something that I knew. Can I find other dots and complete the pattern? So this is the essence of active perception, to set up a goal and have a belief, and then take actions to complete or improve our belief. The action plays an important role here, just like for other kinds of perception. We don't just see, we look. We can't just hear, we listen sometimes. And that is the action. What is cognitively informed agent? In artificial intelligence, an agent is everything that can perceive from environment and act upon it. That can be a very simple thing, like a collection of rules, if-then rules. But such agent will have limited abilities, because how many rules can be defined? With the advent of machine learning, AI systems were improved because now they could extract knowledge from data. But the problem is the perception part is still passive, not the way that humans and most of the animals do perception. Because we usually collect lots of data and process them in a passive form. A cognitive system is an autonomous system that can not only perceive from environment and act upon it, but can also learn from its experiences, anticipate the outcome of events, and adapt itself to the changing circumstances. So at the top of action perception loop, we have another loop for adaptation, anticipation, and assimilation. There are lots of applications for such systems. They have applications in health and well-being, safety and security, and efficiency of life. Here is an outline of my talk today. I will first give you a brief introduction. Then I will cover what have I done so far, what am I doing, and what am I going to do next. A key challenge in the field of AI is actually designing intelligent systems or agents that can understand the state of their partially observable environments. This is something not that difficult for humans and most of the animals because they have ability to reason about their uncertainties. And they can come up with strategies for information gathering. They can easily answer to the questions like where to look, when to look, and what to remember. Unfortunately, this is not the case for most of the AI systems. They don't put actions, and they usually are not like that. They interact with the environment and try to explore it. As I said, they're mostly passive entities. But how we humans do that. In the field of neuroscience, it is nowadays believed that the brain works like a probabilistic machine. It does a kind of inference. When it sees an observation, it tries to solve a kind of inverse problem, goes from the observation to the causes that generated that observation. And there are some challenges that the brain needs to solve. One is uncertainty, which sometimes arises from the noise in the sensor data. The other one is ambiguity, that is based on inherent structure of the problem. That means different states or different causes can generate exact same observation. Now that problem, the inverse problem, will be ill-posed. There is no way to go back from the same observation and infer which state is actually generating it, because two or multiple different states are generating the same thing. Here's an example of noise. If we have a clean data, it is easy to do face recognition or even emotion recognition. But when we add to the degree of noise, solving these tasks will be more difficult. This is an example of ambiguity. When we look into this object from this point of view, there is no way for us to distinguish whether we are looking into this object or this one, because we cannot see this side of it. So this is kind of ambiguity, that the same object is generating, actually two different objects are generating the same observation from this point of view. But we humans are not passive. We can change the position of the object, we can move around it. Why can an intelligent agent be like that? So here is where I'm working on. I was working in the field of computer science and engineering, mostly in AI, artificial intelligence, and machine learning, where I found that AI needs to be more intelligent. Then I looked into cognitive science to see the mental processes, how humans solve these problems. And I studied different aspects of human intelligence, incorporated them in my models. I became even more interested. I looked into computational neuroscience, the neural mechanisms, the hardware part of how mental processes. And I realized AI can also help neuroscientists with giving them some computational frameworks to verify their findings and hypotheses. So I work in the intersection of computer science, computational neuroscience, and cognitive science. My goal is to build smarter models for AI to solve real-world problems. I want to help neuroscientists with interpreting their results, giving them computational frameworks to verify their findings in an objective manner. And eventually, I want to connect the fields and develop assistive technologies for people with mental disorders. I have worked on some projects. The main part of my work is developing a kind of agent model that can actively perceive the environment, not passively. It can learn from experience, anticipate the outcome of events, act and communicate to pursue its goal and adapt to the changing circumstances. Today, probably I won't get enough time to go through all the technical details, but my work has been published. I have applied the agent model for solving some real-world problems, for tuning of the cochlear implant parameters for hearing impaired subjects. This project was funded by NSF, Smart and Connected Health Program. I have worked on projects for activity recognition from multimodal, multi-source, and heterogeneous sensor data. I have worked on a project funded by FedEx Institute of Technology for detection of unusual objects and actions. It's a kind of security and surveillance project. And I have some preliminary results for personalized monitoring of Parkinson's disease patients and autistic children, but there are lots of work to be done in this area. To give you an overview of my agent model, I'll start with the problem, state estimation or inference. So traditionally, it can be modeled using a Bayesian inference, where we have observations over time and we try to infer causes from the observations. But when we talk about active perception, now we have action involved. That means the previous actions can actually change the observations. That can cause different observations. That means, for example, if we choose a different path, we will see different observations. That is the outcome of our action. The environment probably hasn't been changed. And that will make the problem NP hard, because now we have actions involved. We can do infinite actions and get so many different observations. Here is an architecture, high level of the architecture of my model. For those of you who are familiar with AI systems, you can see that it is a closed loop system that can get feedback from environment. It does not require supervision or reinforcement. Most of the current agents in AI require at least reinforcement. It can adapt to the environmental changes. Here is a high-level pseudocode of my model, and the main thing here is that in a loop, iteratively, we try to actually, with optimizing actions, we want to have better beliefs or perception, and we will update our belief and take another action. That will happen in a loop iteratively until convergence. I applied a single agent model for tuning of the cochlear implant parameters. That is important because nowadays it's usually like the subject needs to have multiple visitations, and there are lots of trials and errors for tuning of the cochlear implant. It's difficult even for highly experienced audiologists because it's totally subjective. So it's important to come up with some models for tuning of the cochlear implant parameters. And my agent model is able to find the deficiencies, like areas of deficiencies for hearing loss, and give insights to audiologists to tune the parameters in a personalized manner for each subject. I apply the same model for tuning of deep brain stimulation that is being used for suppressing tremor in Parkinson's disease patients. Tremor is actually a symptom of Parkinson, and we know that Parkinson's disease is a progressive disease, so it can change over time, it can be worse. It is important that we have an agent that can adapt to the changing circumstances because it needs to adapt itself to the changes. And here we can see that the pattern of the tremor is different for different subjects or individuals. That means it needs to be personalized. We cannot use the same parameters for different people. It needs to be trained over time. But the problem is one agent has some limitation, just like we humans do. We communicate together in order to solve tasks. We work better as a team. So why can't agents do that? Typically in real world, we have multiple agents that are not necessarily working toward the same goal, but they may have acquired some knowledge or they may have some sensory ability that help others to solve their tasks. In essence, we can actually assume that we have a knowledge base which is distributed among agents in the environment, so we can sample other agents through communication with them. I looked into social cognition to solve this problem. It's a kind of theory or hypothesis saying that it's called hermeneutic cycle. That says when we communicate as humans, there is no way for us to go into brain of different individuals or into their internal model and verify whether our understanding of what they're trying to say accurate or not. All we can say is to come up with our belief. We can make a narrative and we can improve our belief with actions, like asking more questions. But still, there is no way for verifying whether our understanding is accurate or not. That means the internal model and brain of other individuals is actually not observable. So there are challenges to be solved, like when to communicate, with whom to communicate, and what to communicate in different situations. And the other challenge is that internal model of other agents is unknown and unobservable. The internal model of other agents can be changed for different reasons. It can be intentional. The agent itself wanted to change the strategy, or it can be due to external reasons. And not all agents are equally informative in different situations. So communicating with an agent which is less confident or less informative can actually reduce the confidence and accuracy of the current agent. But having said all of them, communication is still useful and it's worth doing that because it can make causal knowledge acquisition more efficient. That means the agent can actually extend its perceptual field and see part of the environment which is not within its field of view. Just like for us, we can observe this room, but if we want to get information about another room without going there, we can communicate. Through communication, an agent is able to acquire high-level knowledge. That will make the model more efficient. That means each agent does not actually need to process all those low-level information or observation by its own. It can just ask for something and get some answers without doing the analysis by its own. And knowledge sharing and exchange can actually help the agents to find out if there was a change in the dynamic environment. Like if you have multiple agents, one of them is faster in figuring out there was a change, it can inform other agents. So it will make the process faster. It's not like always we'll look to come up with new models. We will first look into the literature and see if there exist models. There are models for state estimations, of course, but as I mentioned, they are all passive models, like hidden Markov model, Kalman filters. There is no action involved in the perception process. There are communication for state estimation, but the problem is that communication strategies are actually not trained, not learned. That means they either use periodic all-to-all communication, some of them use predefined protocols, some communicate with a central system, which will make the process much more expensive. There are some event-triggered communication protocols more recently that actually help the agents to broadcast their messages or information about the state whenever there is an error. So this will help with the problem of when to communicate, but still they broadcast to all the neighbors, so they don't know with whom to communicate and what to communicate. Here is the model of my agents. We can see two agents here. If we assume that the first agent is a 1, similar to the hermeneutic cycle, everything behind this interface is not observable for the first agent. All it can see is the observations that come through the sensor. And all it can do is to change the environment through its actuators or effectors with actions. And the other agent will see these changes in the environment through its own sensors and the observations. But the internal model and beliefs of the other agent is not observable to the first agent. So I considered other agents to be active parts of agent's environment, and the agents can control the other agents via changing the control state with asking for help or with communication. I modeled communication as an action in this framework. The problems or the challenges for the agents were that the outcome of action, the received communication message, is not deterministic. That means like we can ask for help or ask a question, but we don't have any control on other agents. Probably they won't give us the answer we were looking for. So it is probable we need to consider it in our model. The other thing is that the number of agents that we need to communicate with is not priorly known. We don't know first how many agents we need to communicate with. So that will make the problem even more difficult, because if we don't get the answer that we were looking for, or we won't get any informative answer, we will have to communicate more. And that all agents are not equally informative. So the policy needs to be, the policy that means with whom or what to communicate, needs to be learned online in an unsupervised manner. And the important thing here is that the agent needs to assign a degree of trust to the other messages. This cannot be other agents, because one agent may be informative in a situation, but it can be totally useless in another situation. If we give a degree of trust to one agent, we may miss information for the situation that they're useful for. So we need to assign a degree of trust to messages, which will make the problem more difficult, because we can get infinite type of messages. I solved the problem using a framework that is currently believed how the brain works. It's my objective function is variation of free energy. It is known as a unified theory of the way that the brain solves the problem. And I solved this dual optimization problem to update my beliefs and choose the actions. My actions shape to my beliefs, and my belief helped me to choose the best action. And this needs to be done iteratively. I answered to the questions like when to communicate. That was the easiest part, because what we want to do is to reduce the uncertainty. If we start with a uniform distribution of belief, that means we don't know anything about the environment. We sequentially choose our actions that we assume, or the agents assume, are the best, and we improve our belief to converge to certain states. The problem with whom to communicate was a little bit more difficult. That means the agent needs to have more components. That requires agents to have a model of environment that help it to interpret its own sensory observation. It needs to have a model of other agents to predict their behavior, whether they are going to be helpful in certain situation or not. It needs to have a prior knowledge about environmental state. That means how they look like, how many states we have. And it needs to learn a policy for whom to communicate with in different situations. Like if this is current belief, with whom to communicate at this time. And at the end, it needs to predict the upcoming message. That means it needs to have the ability to map its information in the state space to the observation space. And that is a must for having a closed loop system, because what we want to get is the error. We want to minimize the prediction error. So we need to have the observation in its own space that gives us a feedback whether the prediction was correct or not. Here's the demo of how the model works. If the task is activity recognition, assuming each of these dots are an agent. So each agent, let's call this one a head agent, has access to a 3D point or 3D axis for the movement of, for example, the head. It cannot see the movements of hand. So if the head is fixed, but the rest of the body is moving, there is no way for this particular agent to say what the activity is. So it needs to communicate with other agents. And each other actually agent has access to a 3D point again, not the observation from other points or parts of the body. And this is how it solved the problem. The head agent solved the problem. It will communicate with other agents in different parts of the body, mostly this part, to converge from something like a uniform distribution of not knowing what the activity is to the correct activity, which is knocking. And this is how the agent sees the observation and the belief, or the distribution that is trying to be converged. It starts from a uniform distribution, almost uniform distribution, with choosing the best agents, or the agents that the head agent thinks are the optimized one. It will improve its belief until converging to the accurate activity, which is not. I applied that model for detection of freezing of the gait in Parkinson's disease patients. Freezing of the gait is a sudden and transient inability of moving. That can be dangerous because the person may fall because it cannot move its muscles. And because Parkinson's disease is progressive, again, it is important for the agents to be online, and it needs to be personalized. The other thing is that it always doesn't start from the same part of the body. For some people, it may start from like leg and go to the trunk, or vice versa. So it's desired to know what is the nature of that process for different patients. Communication will help with that, because if you start with an agent and it communicates with other parts of the body, that means the problem is actually developing in the body. And the other thing is different modalities of the sensors may have different types of information. For example, if the person had gotten freezing of the gait while walking, the accelerometer can be more informative because it shows the movement. Or the position is also important. For example, the sensor in the leg can be more informative. The problem of what to communicate. Let's say we have agents that are trying to monitor houses with different layouts. People with different lifestyles are living there. And the sensors in different houses are totally different. For example, in this house, we may have a front door sensor, and in another one, we don't have that sensor. So if one agent is monitoring the first house and the other one is doing the second one, there is no way for them to communicate, because if the first agent says front door sensor, the other agent doesn't know what it is. It hasn't been defined in its vocabulary. It doesn't have any idea about that. How can they come up with a common vocabulary or common language to communicate? Is the problem we're trying to solve in this task. So I came up with the idea of meta features that gives the agent some features like, for example, location or functionality of the sensors or time of the day. And what they need to do is to map their own observation to these meta features and go back from the belief and their own observation to the meta feature and communicate, find the best features to communicate with the other agent. That mapping is being done here. So the action here is to choose which meta feature to use and in which order to communicate. What am I currently doing? So far, as I mentioned, I have modeled the task of communication or perception, actually the active perception, using actuators. I assume communication is an action, so the agent can change the environment through effectors or actuators. But there are theories in neuroscience saying that that's not all. When we are trying to solve a task, actually our sensory system is also being tuned to be able to solve that task. That means it will be more selective toward that task. We see what we want to see. So the other thing is the interpretation model. That means maybe the message that I got is not what I was looking for, but what if I can still use, for that, I need to be able to map that feature or the message with my prior knowledge somehow to interpret it and use it for my state estimation. That will make the process more efficient. So what I did was, I'm actually doing this to add 2 other blocks to my existing system. One for the sensory model. This is actually coming from data of ferrets that shows the animals will be more selective toward the task that they are trying to solve. Like if this is called tuning curve of the neuron of that animal. And when they're trying to solve a task, that will be tuned somehow to solve the task more efficiently. And after they're done with that task, it will go back to the way that it was. This is called short-term plasticity. And for solving the interpretation part, I am actually modeling it as a graph that can connect the features to the previously known features. So it can give the agent the ability to interpret the new upcoming messages and map them to the other features. We have publications to be appeared. The other thing, project I'm working on, which is relevant, is the attention in human beings. So there are 2 different hypotheses about how the information is processed in the brain when we are paying attention to something. Some researchers believe that it happens early. For example, if it is a kind of auditory attention, it works like a filter. We won't hear or we won't get that information if we don't need it. It will be filtered in earlier stages like in cochlea. But there are other researchers that believe that we will get all the information, but it works like a decision making. It will go to the cortex, which is higher level in the brain, but we will decide to ignore part of the data. So we are collecting data from human subjects to see which one is explaining the behavior. We know that the early selection happens, but how can it interact with the late selection part and how they work together, whether there are scenarios that late selection is more useful, is the things that we're currently doing. What am I going to do next is to extend my proposed autonomous agents architecture to incorporate more aspects of intelligence, to develop personalized assistive technologies for people with special disorders. This can be done in different ways, with continuous monitoring of mentally ill individuals to facilitate proactive actions like alerting a caregiver before something bad happens, or using a smart virtual agent for diagnosis and therapy of psychiatric disorders. The other direction that I'm interested in is understanding underlying mechanisms of mental disorders. For example, currently we are studying attention in a typical brain. But what is different in an atypical brain, like people with attention deficit or autism, that make the attention process different for them? So the work that I have done has potential of bringing grants from different federal resources like NSF and NIH. Now I'm giving you a brief overview of my teaching experiences. During my graduate studies, I have experience of co-teaching a course, Introduction to Artificial Intelligence. The topics I covered were utility theory, beliefs, uncertainty, decision networks, and value of information. I looked into actually sequential decision-making problems like Markov decision processes and partially observable Markov decision processes, and the solution to them like value and policy iteration and like online algorithms for solving the problem. And I gave a brief introduction about multiple agents, decision making when we have multiple agents in the run. At Johns Hopkins University, I was a guest lecturer and course assistant for audio signal processing. I covered topics like audio compression and affective audio signal processing. And I was involved with the evaluation part. I wanted to improve the critical thinking in the students. So I came up with the idea of building some forums and encouraging them to participate in discussions. I introduced some papers, some recent publications in the field of audio signal processing. I wanted them to choose their topic of interest, read the paper, and write about their perspective, what they understand, what they think are strengths and weaknesses of the paper. And I wanted other students to go through the discussion, participate there, and write about their perspective, ask questions, and put comments. This is how one of the forums looked like. And actually, throughout the semester, I wanted them to work on projects in group. This course was a multidisciplinary course. We had students from different departments, like in computer science, biomedical engineering, even art and acoustics. I wanted them to work into different projects as a team. And the interesting part was they worked as a team, and at the end of the semester, when they were presenting their findings, they were able to say how they collaborated and how they put the pieces together. People from different departments were able to solve interesting problems from healthcare to music and speech recognition. These are some sample topics. And my lectures in this course were actually recorded to be used in an online course to be delivered at Johns Hopkins University. And I also have experience of teaching courses like signals and systems. In that, I held recitation sections to make sure that the students were following the course and were able to get all the details about the topics. And I have experience of teaching about artificial intelligence to K-12 students during 3 consecutive years. Thank you so much for your time and attention. Please let me know if you have questions.
So I think your research is really interesting. You're really working on a really high level inverse problems
Thank you.
with, because in geophysics, which is, I have a background in, we work in inverse problems, but it seems like, you've added a feedback loop with the artificial intelligence. And I'm just, and a lot of this is applied to humans. And I'm trying to look at this and imagining if there's a better way that we can do inverse problems in physical systems. Anyway, we'll have to have a discussion later, maybe.
Sure. Yeah. Actually, my research interest has been healthcare. That means I've worked mainly in health area, and this is something I want to continue. But the applications of my model is not restricted to healthcare or any other area. That they have applications in different fields. And I'm pretty sure it will have applications in geophysics and environmental side. But the thing is, we also get ideas from physics because most of these free energy and these concepts are actually coming from physics. So the feedback is something that AI is adding, like to make it more accurate, to get feedback from the environment to make better decisions. But most of the concepts are coming from math and physics.
Yeah, it's interesting.
Yeah, I noticed the notation on the notation that you used is more common in physics.
It is. Actually, I tried because my publications were supposed to go to AI. I changed it a little bit to be more understandable to AI. But when I was trying to understand them, they were coming from physics. I went through that literature.
Yeah, so can you comment on like models for your agents? In order to make those tractable, how often do you fall back on are linear? You didn't talk at all about linearity or.
Yes, actually, in these models, we assume that the agents have a linear model. That means the mappings were linear, but it can be kind of piecewise linear because we have multiple models. But we showed that eventually, because we incorporated communication and feedback, even a simple, simple in terms of number of parameters and being linear, model can get accuracy like nonlinear systems, CNNs. We compared with them in our publications. We get accuracy in that level, but the models were much more efficient because of those kind of linearity, less number of parameters, because now everything was distributed among agents. And the other assumption we made was that we assumed noise does not have information. That means the distribution is Gaussian. That was another assumption.
Yeah, that may be.
So you deal with the same issues, non-uniqueness, all the problems that you deal with inverse problems. And I mean, sometimes a little bit of noise can be helpful. You find that to be the case?
When we're working with other agents, there are always noises. We have different types of noises. And if it is something that is happening all the time, like it is the long-term behavior of the agent, so the other agent are able to interpret that noise. So they know that this is coming from a particular agent and this is part of it. They know how to interpret it. But if it is something that is happening in short term, that means that can happen also, for example, in the case of cyber attacks or noise like that, which is more like an outlier. In those cases, because it is getting feedback from environment, it can ignore that part of the noise or that part of the information. So it moves to another agent. Sometimes noises happen because, like, if some agent want to help another agent, so a third agent may see that as a noise because of its own sensory ability. With these types of noise, the agents can see.
I have actually a ton of questions, so
Sure.
I don't know if we have enough time. We can take that offline as well.
That's
So
fine.
first thing is you talked about NP completeness at some point.
Right.
We all know that lots of things in computer science are NP complete, and at the end of the day, we use greedy algorithms. Do you have any comments on that? Or?
Well, yes, actually, that is the point, that we don't want to use greedy algorithm. That's why we learn a policy and choose the optimal action. We want it to be more like optimized compared
So
to
it's
completely greedy.
optimal or it's optimized? Because optimal
Optimized.
means
When we learn the policy, that means we're optimizing the parameters of that model in order not to be like a greedy method.
And
So
is theory about approximation to NP completeness somehow helpful?
Helpful, you said?
Helpful.
Yeah. We showed that, like, with the policies learned, and we compared this with different scenarios, like when it was not learned, how it will perform. Like, we actually evaluated the model and compared it with the scenarios that the policy was not learned, it was predefined, or it was totally random, or it was learned with a greedy approach. And in these cases, our results show that the model, learning the policy will help in different scenarios. Like, for example, first of all, if there is a change in the behavior of the other agent. So now that we are learning the policy, we can track it. So we have a model of other agents. It is not like a random thing. It will be helpful there. Or because the outcome of action is not deterministic. So if you get a message which is not as expected, the agent has the ability to move to the other agent. So it will ignore that useless information. It won't be confused with that part of the information. So it will make everything faster, the convergence will be faster, and the results will be more accurate.
Okay, great. So if I may, next question would be, there's a trend in AI, which is the explainable AI.
Right.
Particularly important for healthcare.
Yes.
Because you need to explain why someone has cancer and why not, right? Can you comment on explainable AI in that field? I mean, if you get at the end agents which can do a great job, but you don't understand what they're actually communicating or what are the categories they're optimizing for. Whatever,
Right.
right? You don't really, yeah, you cannot use that anymore.
That's the problem that I have thought about when I was working with probabilistic models, because in AI or machine learning, it is known that usually neural networks are like a black box. So when we solve a problem, there is no kind of interpretation in that. So there is no way for people to trust. Even like we human, when we communicate, if something like we'll get an end answer like this is the best, there is no way for us to verify. We won't believe. So when we communicate and when we use like models like probabilistic models, we have a level of interpretation. Like for example, if we have different causes, now we connect them together. So we have a level of, I mean, it's not a verbal communication in my model, but because there is a communication, we see the causes, we see which agent we communicated, so we can track and have a kind of interpretation. But that can be.
Okay, good. And still, next question. Yeah, it's plenty of science you're presenting, so
Sure.
yeah. Game theory
Okay.
is all about agents seeing each other as adversaries.
Right.
These agents are somehow supposed to cooperate, right? And they're built to be cooperative. What happens if you replace one of these agents by a malicious agent, or have you thought about that?
Sure. Actually, that is the thing that we try not to assume the agents are cooperating or competing. That's why we say that we have agents in the model, not necessarily working toward the same goal, but they can still help each other in different situations. So when we learn a model of the other agent, that means we can have a prediction of the behavior. So if we could interpret the message that we got from the agent, like I expect some particular agent can help me in this situation. I ask for a message. If the message is as I was expected, it reduces my uncertainty, I will go with that. Otherwise, I'll have to ask another agent.
Okay, good. Okay. Finally, now about teaching. You've done quite some things with audio processing and which is fun to teach and fun to learn, of course, and other things, even AI. Our bread and butter at UAA, of course, is more like Introduction to Computer Programming 1. Do you have any kind of experience there, or I mean,
Yes.
operating systems or the standard, trivia of computer science, right?
Right. Actually, I did my bachelor in software engineering, and there I had the opportunity to work with different programming languages like C++, Java.
Okay.
And then in my graduate school, I worked with MATLAB and R and Python in order to compare my models with different like deep learning approaches. They're already implemented in Python. So I use that language. I am familiar with programming languages. And the courses like operating systems for computer science courses I've passed during my bachelor because it was software engineering is very closely related to computer science.
Okay. Thank you.
Thank you.
Hey, can I ask a question? Can you hear me there?
Yes, sure.
Super. Thanks for the presentation. I missed the very first part, so I apologize if you covered this already. But you talked a little bit about cochlear implant training those devices, and I guess I just didn't make the connection between the agents and the communication and if it was that the same kind of model that you were applying to the cochlear implant devices, or was it a different? Sorry, or was it a different model?
For cochlear implant and to tuning of deep brain stimulation, I used a single agent model. So one agent model was used for tuning of parameters in cochlear implant and DBS application that I was talking about first. Then we actually worked on the model and added other agents. The problems that we solved with them was that multi-model, multi-source activity recognition and monitoring houses. Those examples were when I talked about the communication part. A single agent model is for cochlear implant.
Great, super, super. Thanks very much.
Thank you.
I got a quick question for any of these problems, any of the simplified problems, are you able to get a certain do exact analysis or?
There are approximations that, like, for example, linearity and the Gaussian assumptions for the noise.
Mhm.
And there is one more approximation for objective functions. When we work with probabilistic models, it is hard to optimize the model or get the answers because it is NP hard. Like in POM-DPs, it will grow exponentially with number of actions and the states. And it is partially observable. Now we don't have the states. So in order to solve that problem, I use that objective function coming from the neuroscience part that says this is how the brain works, and it's a kind of variational approximation to solve the probabilistic problems, like the models that are built in a probabilistic framework. So that will help us. That is nowadays being used in machine learning under some models like variational autoencoder. That will help to optimize the parameters of probabilistic systems with a kind of optimization problem, like optimization model, like gradient descent. So building that optimization function helps us to solve that dual optimization of action, and we use variational inference for that.